When we are designing a battery pack, that means that we're going to have to determine what is the voltage, nominal voltage of the battery pack, what's the nominal current, 1C rate, if you will, of the battery pack, what's the energy, what's the power, how many cells in series, how many cells in parallel, how large should each cell be. All of these kind of characteristics. I'm not even thinking about the thermal characteristics and so forth, which are also very important. We want to be able to get a pretty good idea of the size required for that battery pack before we start building anything. Batteries are expensive, and engineering time is expensive. Building circuitry is expensive to prototype, so it's important to be able to simulate the pack as well as the application that the pack will be used in before going too far down your design path. And so this is going to help ensure that the pack is going to be able to meet all of the performance requirements before we make a very large investment. We've talked before of some of the applications of large battery packs. We could look at grid storage. We could look at frequency regulation. We're going to continue by looking at the electric vehicle space, xEVs, different kinds of electric vehicles. Looking at the space, to predict the battery demand, we would need to simulate the load, which is the vehicle. We would need to simulate the vehicle over real-world operating scenarios to see the profile of power versus time or current versus time that is demanded from the battery pack by the vehicle. Last semester we did see things that were called UDDS profiles of current versus time. It was an urban dynamometer driving schedule. This is now where we see how we arrived at those profiles. We're going to see that the UDDS profile is actually given as a profile of vehicle speed versus time, and we had to simulate a vehicle and a battery pack in order to arrive at current versus time derived from speed versus time. There's a whole range of electrified vehicles, starting at hybrid and ending up at battery electric vehicles. We are not going to look at hybrid electric vehicle simulation here. These simulations are very complex because to simulate a hybrid electric vehicle you have to simulate not only the electric system but also the internal combustion system. So we have to simulate the engine and its profile of speed or RPM, I guess, versus power and so forth. Always for an internal combustion engine there's a multi-speed transmission. For a hybrid vehicle there's going to be some kind of a control algorithm that determines how to blend the electric power and the chemical power from the combustion engine, and all of these would need to be simulated accurately. And a lot of things, such as in an automatic multi-speed transmission, what is your shifting profile? That's proprietary. Different vendors would have different ways of doing that. Your hybrid blending control algorithm would be proprietary. Your internal combustion engine controls would be proprietary. You may be able to get a pretty good map of how the engine works, but the actual details would be proprietary. So it's complicated, and we would really need a lot of very specific information on how the vehicle worked to do it well. Now that said, there are simulators that do that. Some years ago, when I began research in battery systems, the National Renewable Energy Lab sponsored a program where they made something called Advisor. And that stood for something, I don't remember what any longer, but that was a hybrid electric vehicle simulator that ran in MATLAB Simulink environment. And that has since been orphaned by NREL, but it has been picked up by some for-profit organizations, and you can still get updated versions of that. I want to say that it's AVL is the company that sells it. That may not be right. But it's possible to do these simulations. It's just very challenging to do so, and you might need to spend some money on a simulator that is going to do that for you. We're going to look at a simpler problem. We're going to look at a pure electric vehicle simulator, which also corresponds to what a plug-in hybrid or an extended range hybrid would be doing when it's operating in electric-only mode, when the internal combustion engine is off and it's simply running on its motors. These simulations turn out to be quite straightforward. There's no internal combustion engine. The transmission is generally a single-speed fixed ratio transmission, just a gearbox really, and there's no blending of power sources because only one power source is being used. To simulate an electric vehicle, then, we need two things. One of these is an accurate description of the vehicle, and there's some fairly detailed information that's required, and we talk about this in a minute. But these are things that you can guess reasonably accurately, even if you don't know what the vehicle is, just by comparable vehicles on the market that might have some of these characteristics published. So this here, you can get that data. And then the task the vehicle is required to accomplish. This is the profile of speed versus time, for example, that the vehicle is required to meet. The vehicle description includes battery cell characteristics. How do I combine those battery cells to make modules? How do I combine modules to make battery packs? What are the characteristics of the motor and the power electronics that drive the motor? What are the characteristics of the mechanical drivetrain? And so forth. And we'll see many of these, not this section, but next section when we talk about the equations that describe the model of an electric vehicle. The vehicle task is a drive cycle. It's vehicle speed versus time, and sometimes we also include in that a corresponding road grade, or the angle of the road versus time. Some examples are the Urban Dynamometer Driving Schedule, UDDS. We've seen that before. The Highway Fuel Efficiency Test, HWFET, the New York City Cycle, and the US06 Drive Cycle. This is what's used by the automakers to determine their fuel efficiency of a regular vehicle, not an electric vehicle, but a regular vehicle. They stick the vehicle on a dynamometer, and they require that the dynamometer drives the wheels according to the UDDS profile of speed versus time, and they measure fuel efficiency for city driving. The EPA has dictated that requirement. And then for the highways, the highway fuel efficiency, they use this one, HWFET. So these are standard EPA kind of things that the automakers use all the time. New York City Cycle was one that's a bit more ad hoc. It was gathered driving around New York City. I think it's more of a taxi cab or a bus route kind of schedule. There's a lot of stopping and starting and low speeds. And the US06 is more of an aggressive cycle that was recorded by National Renewable Energy Labs near Golden, Colorado. If you have any idea of the topology of that area, it's quite mountainous, and US06 is quite a mountainous, twisty road, but with fairly high speed limits. And so the vehicle was able to get high speeds with high accelerations, and that one actually is usually accompanied with road grade versus time also, even though I don't necessarily consider that part of the profile here. The drive cycles are provided at some profile rate. They will be on the course website. The profile rate is 1 hertz in this case, but you could sample more quickly or less quickly. And I've plotted the speed versus time of the different cycles so that you can see there's really quite a lot of difference in how they operate. And their different lengths of time and so forth. So the UDDS profile is urban, so there's a fair amount of stopping and starting, but once in a while you get up to fairly high speeds when you're on kind of an expressway. These are in metric to try to maintain some compatibility with the rest of the planet, but I know that miles per hour are more familiar with many of you, so right around here this is about 55 miles per hour, is about 90 kilometers per hour, and 60 here, this is about 40 mph. So we peak out at around 40 miles per hour, maybe somewhere between 25 and 40 miles per hour for most of this. So there's a lot of stop and go in the urban environment, but there's some high-speed stretches. So the stopping would probably be at stoplights or intersections, stop signs, or whatever. The highway fuel efficiency test, you can see, well, we're spending most of our time between about 55-ish and about 60-ish miles per hour, which is kind of standard highway driving. We did accelerate at the beginning from our on-ramp onto the highway, merged in, and then there was some slowdown because I guess we arrived at Los Angeles right around then. I don't know. So that is our drive profile for the highway. The New York City cycle, you can see if I look at, that's 40 kilometers per hour and this is 40 kilometers per hour. It's a lower speed profile than UDDS. Much more time spent stopped, and the acceleration rates are actually, I believe, higher. It's probably some New York City cab driver who's very aggressive driving when it's at all possible to do so. And then the US06, we can see that the maximum speeds are quite high. This here is about 75 miles per hour right here. So that is the maximum freeway speed limit in Colorado right now. But there's some at around 60 miles per hour, and then there's other places also, because US06 does have urban portions and it has straight portions also. So it's kind of a combined profile. It's probably the hardest, most difficult profile of any of these to follow because of the power demands at the high speeds. But that gives you an idea, I hope, of this is the input, or one of the inputs to our vehicle simulator is speed versus time, and then we have to figure out how to achieve that speed versus time using battery energy to do so. So all these drive cycles use the same basic equations that describe the vehicle, and the approach is to compute on a second-by-second basis desired accelerations in order for the vehicle to achieve the next desired speed in the profile. And so from the desired acceleration, we compute the force that the vehicle would have to apply at the wheels, the wheel-to-road force, and therefore the torque required and the power required to drive that torque. Now those are all desired in order to exactly meet the profile, but it turns out the vehicle has limitations with its design components. So the desired torques may not be achievable, the desired power may not be achievable because there are specifications on the motor and the battery pack, and so the achievable torque and power may be smaller in magnitude. And so we take the desired torques and powers and we limit them to the maximum achievable torques here, and we get these achievable torques, and therefore achievable road force, and therefore achieved velocity, and this will not always match the desired velocity because of the limitations of our components. We compute battery power based on motor power, and battery state of charge is updated, and over the course of the profile, the battery state of charge is going to go down, and the projected range of the vehicle can be extrapolated by how much the SOC goes down per drive cycle. And a drive cycle has a certain distance associated with it. You just integrate speed versus time to get distance. In the model that we will develop, we could look at different types of motors, and this is not a motors course, so I don't talk about that too much. We are assuming an AC induction motor model, which is not necessarily the most common type of motor used at this point in history, although it looks like it probably will win eventually because it can be made more cheaply than the other kinds of motors that are presently used. You could have a DC magnet motor, you could have an AC induction motor. There's different types of motors. This one hasn't been used so much to date because of the power electronics being expensive, but we expect that as demand goes up, the electronics prices goes down, as is typical for electronics, and that these will end up being less expensive and give better performance than a DC motor. DC motor also requires a permanent magnet, which uses expensive materials found mostly in foreign countries, and so that has some automakers concerned about their use. In any case, we could use different models. We do use an AC induction motor model here, and the AC induction motor has the characteristics shown in the plot where up to a certain speed the motor is able to produce full torque, and in this case the full torque, L max, is about 275 Newton meters. And then at this rated speed, the motor is no longer able to produce full torque. The torque starts to drop off, but we produce constant power. And power equals torque times RPM. And so this is a hyperbolic equation then, because I'm plotting torque versus RPM. And so that's just like a 1 over x kind of drop-off in the power. And this continues until we get to a maximum RPM for the motor. In this case, it's 12,000 RPM for this example. And the breaking point is at the so-called rated RPM. For this motor, it was at 4,000 RPM. This picture, in a nutshell, shows why electric vehicles can be really exciting to drive compared to an internal combustion vehicle. An internal combustion vehicle has a torque versus RPM curve that looks something like that, except at lower RPMs. So that this might be at about 3,000 and this might be at like 6,000-ish. Depends on the engine. So you have to have your internal combustion engine operating at a relatively high RPM before you get your maximum torque and before you get your maximum power out of it. This is why we have a gearbox and a transmission in the internal combustion engine, because if I didn't, I'd be operating extremely low torques at low speeds, and I'd only get good power at high speeds. And so we use gearing to kind of make this 3,000 RPM within the range of operation at whatever speed I'm driving the vehicle. I just gear it so that the engine is always operating somewhat close to its maximum power. At least it's operating maybe around here in the decent power range, and I can accelerate to get the maximum power if I want. But the acceleration from zero is pitiful. It's really, really low. So we have to design way overpowered engines to get this desirable acceleration from 0 to 60, whereas for the electric motor we don't need that at all. For the electric motor we can have a lower equivalent powered motor and we have all of the torque available from 0. In fact, even for a relatively small electric motor, you're probably going to need some kind of traction control on it so your wheels don't slip when you floor the accelerator pedal at 0 RPM. So electric vehicles, if properly designed, now not all of them are, but if properly designed, can be really exciting to drive, a lot of fun. Anyway, that is the characteristic of our AC induction motor, and also because of the fact that the motor can spin very quickly, and we've got all of the torque from 0, we don't usually, in fact, I've never seen a commercial vehicle have a multi-speed gearbox. Tesla did look at it for their one of their vehicles, but they decided eventually not to go and do that because the torque was so high they kept breaking their gearbox, is what I remember hearing anyway. Might not be true, but that's what I remember hearing. So they ended up with a single fixed gearing, as do anybody I've heard of for an electric vehicle. And we just operate continuously over this range. So no transmission is needed. That is a huge expense in most vehicles, and so eliminating that expense is great. We do need to gear down, because if your motors were spinning, if your wheels were spinning at 12,000 RPM, you would be going extremely quickly. They're probably going, well, I don't even know what they're going. So no, I think you probably like a 6-to-1 gearing ratio would be what you'd probably use for most cars, something like that. In any case, we are going to look at the equations to simulate a vehicle in the next section, but here's a pictorial overview of what we've talked about on this page of notes. We said we start out with a desired speed from our profile of speed versus time, either UDDS or New York City Cycle or whatever. And from the desired speed compared to the present speed, we get a desired acceleration. And that leads us to be able to calculate a desired road force. And from that, we can compute a desired motor torque. There's limitations to the torque we can produce, so we limit the torque based on what the motor maxes out at this RPM, etc. And that then lets us to compute an actual force, an actual acceleration, and an actual speed. And notice that these are comparable to each other, and we have a loop here that is basically a feedback control loop that tries to match as carefully as possible, closely as possible, the actual achieved profile of speed versus time to the desired speed versus time. In this simulation, the torque that the motor produces requires a motor power, and that will require certain battery power, which will then change the battery SOC accordingly. You can see that even though we know that the battery will place limitations on what is achievable based on what its present SOC and voltage and so forth are, that is not considered in this simulation. So this simulation is simplified a little bit compared to what would be true in practice, but at least gives you a back-of-envelope kind of idea of vehicle range and operating characteristics. So we're not taking into consideration limitations based on batteries. If we did, we'd have a branch that goes here and basically does all the way out to desired battery power and then limited battery power and so forth. Okay, that is the introduction to our vehicle simulator. In the next section, we will look at the actual equations that implement the simulator and some results from some simulations.